Hello, this is Dr. Teskey. I'm going to be rounding out Chapter 9, which we're covering alkynes in this third video. So this is Lesson 3, and we're looking at Section 9.9, which is the ozonolysis of alkynes, 9.10, which is alkylation of terminal alkynes, and 9.12, which is going to be synthesis strategies. And so let's continue our lessons. So ozonolysis of alkynes. We have two scenarios here where we have the ozonolysis of an internal alkyne. So you have two R groups here and here. On the two ends of the alkyne, introduce ozone followed by water, and that what you'll get are carboxylic acids. Now what you're probably realizing that this is very similar to the alkyne ozonolysis. There are two differences. One is that with the that this is very similar to the alkene ozonolysis, and there are two differences. One, with the alkene, you use a reducing agent such as DMS instead of water. And then the other big difference with the alkene ozonolysis that you learned in Chapter 8 is that you're making a ketone and an aldehyde. For this, we are making carboxylic acids. However, it's always different depending on if you're doing an internal alkyne or a terminal alkyne. So in the next situation here, we have a terminal alkyne. Adding in ozone followed by water, you will get your carboxylic acid. But instead, you'll also get CO2. And so that would be the big difference there. So how is this reaction working? I think the best way to demonstrate this is with actual examples. And so if we go to the next slide here, what we're doing, without going through the mechanism in this situation, since we went through that in Chapter 8, so using these examples here, we're adding in ozone followed by water. And what we're doing essentially is cutting this bond. I was going to try to draw scissors, but we're cutting this bond here. And that's what you're doing with ozonolysis. You're doing a cleavage and you're oxidizing. And so cutting at the alkyne and then adding in oxygen on a double bond and an OH on each of those carbons. And so then you'll yield this carboxylic acid plus one other carboxylic acid. So in this case, this was an asymmetrical alkyne. And so you're getting two different carboxylic acids in the end. What about another example? So again, we're adding in ozone and water to an alkyne here, and we're cleaving at that alkyne. On this carbon on the left, you add an O double bond to that carbon and then an OH. And then on this other carbon, you're adding an oxygen double bond and an OH. And so you're opening up this ring. In order to form, and I think the easiest way is to kind of draw it still in that same shape so you don't miss any carbons, or you can go through and count all your carbons. But you have one, I'm ignoring the carbon that has the carboxylic acid on it right now, but 1, 2, 3, 4, 5, 6, 7, 8, 9. And so you can add the carbon with the carboxylic acid, and then you have 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you have your carboxylic acid. And so make sure that adds up. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that is your final product. So you opened up that ring, and now you have a very long carboxylic acid with 2, on each end. So those two were examples, one with the asymmetrical alkyne, and then you also had the a ring opening situation. You do have the case where you have a very symmetrical alkyne. So again, let's predict the products of this. You have ozone and water being added, and so that means I'm adding an oxygen double bond to that carbon with an OH, and then the oxygen double bond onto that carbon in another OH. And so what you're noticing probably is that both sides of that molecule is exactly the same. And so you're getting 2 of the same carboxylic acids. So this is highly efficient because you're yielding 2 of the same molecules with these symmetrical alkynes. And so this is really useful for preparing carboxylic acids. Only one product is formed and you have 2 equivalents. You're not working in the situation where, in those previous problems here, or this one previous problem, we had 2 different carboxylic acids. And so this makes the purification much more difficult because you're having to separate 2 different things from each other. Oops, already said difficult, much more difficult with the asymmetrical alkyne. So overall, this is simplifying the purification and increasing yield using a symmetrical alkyne. So continuing with our practice, because I think the best way to learn is through practice problems. And these are just your practice with conceptual checkpoints from your textbook. So let's take a look at this. Take a moment to read it. Okay, so an alkyne with the molecular formula of C6H10 was treated with ozone followed by water to produce only one type of carboxylic acid. Draw the structure of the starting alkyne and the product of the ozonolysis. Okay, so the key word here is one type of carboxylic acid is forming. So we must be dealing with a symmetrical alkyne. Fortunately, we have an even number of carbons, so this is going to be a fairly easy task. You're going to want 2 of those carbons to be part of the alkyne, and then you're going to have 2 carbons on either side of that alkyne. So once you take a moment, draw that out. So what you should have had is CH3CH2, then an alkyne in the center, followed by CH2CH3. So notice how symmetrical that molecule is. We're adding in ozone, followed by water. And we're going to do the same thing that we've been doing, which we're going to cleave, and we're going to add in oxygen double bond and an OH. So cleave, oxygen double bond, and an OH, oxygen double bond, and an OH. And so we get 2 of the same carboxylic acids. That looks like that. How about this next problem? Take a moment to read it. Okay, now that everyone's had a moment to read this, it's an alkyne with a molecular formula C4H6, and it's treated with ozone and water to produce a carboxylic acid and a carbon dioxide. So that's one part of this question. The second part is also asking to do a different reaction. Draw the expected product when the alkyne is treated with aqueous acid in the presence of mercuric sulfate. And so we don't want to be forgetting any of the reactions we've learned earlier in this chapter, and so we want to keep on practicing our skills. So we have an alkyne with a C4H6. We know that we're having a carboxylic acid and carbon dioxide forming, so this must be a terminal alkyne. So we for sure have an alkyne at the end of our molecule, so that's 2 carbons already. And then, since there's 4 carbons in total, we add on that ethyl group. Your hydrogens should all add up. We got 5 plus 1, so that's 6. That's good. And so let's do that first ozonolysis. So add ozone and water. We are cleaving and adding. So add the double bond oxygen, because this is the terminal alkyne, and so we're forming CO2. And then on the other side here, double bond oxygen and OH. So in the end, you'll have CO2, and we could even draw it out like this, plus the other carboxylic acid from the other side of the molecule. So the other part of this question was asking, what happens if we have this same alkyne? So let me draw it again. And we add in sulfuric acid, so aqueous acid, so it's sulfuric acid and water is how we're commonly denoting this, plus mercuric sulfate. So what type of reaction is this? And you should get used to asking yourself, what type of reaction am I doing and what am I starting with? We're starting with an alkyne and we're doing a acid catalyzed hydration reaction. And so what do we form in the acid catalyzed hydration? So your chapter goes through the mechanism. We're not going to go through it now because you've already seen it. But what you're forming is first an enol, which is fleeting, and then you'll tautomerize over to the ketone. So there is an intermediate that is formed. You want to make sure you have all your carbons. For this, I probably should have drawn this the other way, but that's okay. So I have my ethyl here. Oops. OH and a double bond. So this is your enol. Make sure your carbons add up. You got 1, 2, 3, 4. 1, 2, 3, 4. So you're essentially adding on a hydrogen and an OH along that that triple bond, that alkyne, in order to form this alkene. So we added a hydrogen. There's already a hydrogen on that carbon, so that's carbon. And then we also have an OH being added on to this carbon. So we have the OH and H. And this is done in a Markovnikov fashion. Markov, meaning that this OH, the OH needed to be added to the more substituted carbon. And that's what we did here. So we added the OH to this carbon, which is more substituted. Get rid of those numbers here. And then we added our H to the less substituted carbon. So that is the regiospecificity of this reaction. But this immediately tautomerizes into the ketone. So what we end up getting then, so here's the ethyl group, so that's that side of the molecule, so that side of the molecule. So make sure you're keeping track of everything. This OH is going to turn into a double bond O. So basically, you're going like this. Well, this is going to pick up a hydrogen from the acid that's hanging around. And you're going to form this final ketone. So you'll also lose this hydrogen. So that is the product for that. So make sure you're not forgetting your previous reactions. Okay, so 9.10, alkylation of terminal alkynes. Recall that terminal alkynes are completely converted to an alkynide ion with sodium amide. And so sodium amide is basic enough, so it's a pretty strong base. We know alkynes are weak acids, and it has the ability to deprotonate that alkyne in order to form the alkynide ion plus ammonia, or ammonium ion. Sorry, ammonia. Ammonia. The alkynide ion is a stable conjugate base. And we know that because with our ARIO rules that an sp carbon, so a triple bond carbon, has a lot of S character. It has a very short, much shorter bond than alkene and alkyne, and so it's able to hold on to those electrons and stabilize that lone pair of electrons in charge better than, say, an sp2 and an sp3 hybridized carbon. And so this is a very stable conjugate base. This is the O in ARIO, so your orbital. This makes this very, very synthetically useful because now it can be a nucleophile. So that's what we see here. We have a good nucleophile. It can attack some R group. You have a leaving group pop off, and then you form a new carbon-carbon bond. So that's that R group's alkyl, right? So a carbon-carbon bond is being formed. This is behaving in an SN2 reaction. So we're still talking about terminal alkynes here. So alkylation of the alkynide ion is SN2 substitution. And so it works best when we're dealing with a methyl or a primary halide. And that is because of steric hindrance. If you have a secondary or a tertiary alkyl halide, there's not going to be enough room for that alkyne or alkynide ion, which is acting as our nucleophile, to come in and attack the electrophile or the alkyl halide. So let's go through this particular example. You have your sodium amide. It's going to abstract a proton and move those electrons into that carbon. And so you form this intermediate. I guess I don't need to draw that carbon in. 2, 3. I'm going to draw that carbon in so we see what we're looking at. And now we have a really great nucleophile that can attack at that carbon and have the loss of a leaving group, iodine. And so then you form this new carbon-carbon bond in this final product. So you can have two successive alkylations if you start with acetylene. So acetylene has no R groups on the carbon, it's just two hydrogens. So you have to do this successively. So first you add the sodium amide. This is going to take this proton here. And then you add in your alkylating agent. So the alkyl halide. So Ri is it, for example. And then you have to do it again in order to alkylate the other side. So you do have to add do it in 2 separate steps to get that alkylated on both sides of that alkyne. So this is just reiterating that same thing, but showing an actual example. So it's a double alkylation of the acetylene, and it must be stepwise. In this case, you see that they have an ethyl iodine. So once they formed their alkylide ion, so they deprotonated this. That's at the nitrogen there. This can then attack at that carbon in an SN2 reaction and pop off that leaving group. The iodine forms the first product, and then you do it all over again. So I guess technically it was this hydrogen that was lost. And then again, remove this hydrogen and you abstract that proton, and you form the alkylide ion again, and you have methyl iodide this time that you can tack and form this final product. So this is incredibly useful. Complex target molecules can be made just by building a carbon skeleton and converting the functional group. So this is a tool to build and add alkyl chains onto your alkyne, and then you can do other synthetic reactions to get a different functional group. So we're just adding more to our tool belt here on what kind of transformations we can make using organic chemistry. So some examples. Let's start out with starting with the acetylene. Show reagents that you would use to prepare each of the following compounds. So starting with A, take a moment and think to yourself, what is 1-butene? So draw that molecule. So but, we are going to have 4 carbons. 1 indicates that we're going to have the triple bond, or the ine, the alkyne, at the 1 carbon. So we are making 1-butene because we're starting with acetylene. And acetylene looks like this. You can draw it this way. 1, 2, 3. We have the 2 hydrogens off the carbons. You can even draw the carbons in if you want. So let's draw that over. There's your acetylene. We have to say what reagents we'll need then to make 1-butene. Said that we have the alkyne on the 1 position, so that's carbon 1, carbon 2, and we need 4 carbons in total. 3, 4. So that's our 1-butene. So what you should be evaluating here, we just talked about alkylating, acetylene or alkynes, terminal alkynes. What is different between acetylene and the final molecule? The difference is this ethyl group. So we must be adding on 2 carbons. Using sodium amide, we're going to form that great alkylide ion, and then we're going to want to add on 2 carbons. The best way to do that is using this ethyl iodide in order to, as our electrophile. So that's where you're looking for what's different from the product, from the starting materials. So how many carbons are we adding on to this molecule? Let's take a look at 2-hexene. Draw out 2-hexene. So we're going to have a methyl at the end. That's carbon 1. Carbon 2 is where that alkyne starts. We got carbon 3. And then hex means we have 6 carbons total. So we have 3 so far. We need 3 more. 4, 5, 6. So make sure you always, go through and check to make sure you have everything added on, or that you have the right molecule. And we're again starting with acetylene. The first thing you should be noticing is that we have a methyl and we have a propyl group hanging off that alkyne, which here we just have 2 hydrogens. So we're going to have to do 2 successive alkylation steps in order to get the right alkyl groups on the 2 sides of our alkyne. So step 1, we can even do this a little bit different. So 1, 2, if you wanted to, or you can list them all down on the arrow, but 1, you're going to do sodium amide, and you're going to alkylate one side of the molecule first. It doesn't matter which one. I'm going to say I want to add that methyl group on, and so then I'm going to use methyl iodine. Iodine is just a really great leaving group. You can use methyl bromide if you want to. Once I add that methyl group, then I have to do another reaction to prepare my alkynide ion with sodium amide. So that's step 3, and then this time I want to add on this propyl group. So I'm going to add in propyl iodide. And that's how I would form that molecule. So you're probably seeing a pattern here. We'll do one more, round this out. 1 hexyne. So again, your alkyne is going to be in the 1 position. So it's going to be a terminal alkyne, and then you have hex, so that means it's going to have 6 carbons. Okay, and so to draw that, so draw my hydrogen here. So that's carbon 1, carbon 2. That's because carbon 1 is going to have where the alkyne starts. Got 2 carbons on, 3, 4, 5, 6. Make sure that adds up. So that's what we're making. Sorry, I drew that first too far to the left, but that's okay. We'll draw our acetylene over here. This is our starting material. We will need to add in sodium amide in order to first prepare our, so that's step 1, we're going to prepare our alkyne to make an alkynide ion. So I made this. And then we're going to want to add in whatever we need to get 4 carbons on the right side of this molecule. And so that is a butyl group. We're going to have 1, 2, 3, 1, 2, 3. Oops, I need 1 more carbon there. 4. So that's a butyl iodide. 1, 2, 3, 4. So draw this again. We're going to have our great nucleophile come in, attack, and lose our iodine as our leaving group to form that final product. Okay, so it's 9.10. Looking at 9.11, this is where we're kind of applying our synthetic strategies. We have all of these tools in our tool belt in order to do these different types of transformations. This chapter particularly wants you to recognize that there's a lot of ways to convert between alkyne, alkene, alkane, but what about the reverse process? So going from alkyne, alkene, alkane, we're increasing saturation because we're adding hydrogens. So adding, I'm going to put it down here, increase saturation as we go this way because we're adding hydrogens. That's what it means when you're increasing saturation. And so we have, you know, H2 and platinum. So a hydrogenation reaction or a reduction reaction. We have the same thing, hydrogenation with a poison catalyst, so Lindlar's catalyst. We also have our dissolving metal reaction, so sodium in liquid ammonia. And then we also have, again, the hydrogenation with platinum, a reduction reaction. And so we have all these tools in order to increase saturation. Well, what about the reverse? How are we going to do that? So decrease saturation, going from your alkane to your alkyne. And that means that we're removing hydrogens, right? So how are we going to do that? We have halogenations of our alkene followed by elimination will yield an alkyne. And so we kind of have to go in and out, right? We have an alkene, which has 2 hydrogens here. We add the, we do a bromination in the carbon tetrachloride solvent. This is just a solvent. In order to add on our 2 bromines, and we form now an alkane, which now has more, has the 2 bromines, and it has more saturation. So this is an alkane. So alkene to alkane, and then you're going to reduce it or do an elimination step in order to get it fully to the alkyne. And so this is using excess sodium amide and water, and that will get you to your alkyne. So these reactions do give us a handle on interconverting single, double, and triple bonds in this manner. And so this just kind of summarizes that. You have your hydrogenation with a poison catalyst, or your dissolving metal in ammonia. That will bring you to the alkene. To do the reverse of that, you would want to first add in your bromination step, followed by adding in excess sodium amide and water to get to the alkyne. And then right now, we do know how to go from the alkene to the alkane using the hydrogenation reaction. We have not gotten to chapter 10 yet, but we will learn how to go from an alkane to an alkene. But right now, what's important is that we do know how to go from, an alkene to an alkyne. So brominated alkane, essentially, all the way to the alkene, or alkyne. Okay. So I really like what your book does is summarize all the reactions you learn at the very end here. And what I do is I go through each one and I put little notes around it so that it helps me remember what's happening in all of these. Things you want to note are, so let me change colors here, stereospecificity and regio selectivity. And so what do I mean by that? Your stereospecificity will be your anti or syn addition reactions, and regioselectivity would be your Markovnikov versus anti-Markovnikov. You should just say anti-Mark. That's not fitting very well here. Note that this is all with terminal alkyne in the center here. So we have a terminal alkyne, but you want to get used to saying to yourself that if I have a terminal alkyne and I do, say, this reaction, number 4, this reaction, number 4, is an acid catalyzed hydration. So when you see the archaic sulfate and an acid and water, that you're always going to be going from a terminal alkyne to a ketone in an acid catalyzed reaction. So get used to saying what type of reaction you're doing. Get used to saying what the starting material is, terminal alkyne. The product is a ketone. And so then you get used to doing that, you'll start to see, okay, you'll just be faster with the reactions, right? So I guess to show you what I do with this is I go through and just write little notes. So for reaction 1 here, elimination reaction, this is with a geminal halide, dihalide, and then we have the vicinal dihalide. Reaction, and it's also reaction 2, so you're adding an excess hydrohalogens in order to do that, so it's a hydrohalogenation. And then you can also go for your geminal and vicinal dihalides and go to the terminal alkyne. Other things, so reaction 3 here, which is your hydrohalogenation. This is going to be a Markovnikov addition. And you can even know, okay, so Markovnikov, we're going to have 2 different things that's being added on. You're going to have your halide, which must be added on to the more substituted carbon, and you're going to have a hydrogen being added on. We already kind of went through reaction 4, this acid catalyzed, but more information to add to this is that it's a Markovnikov. So you're adding 2 different groups. You're going to have your an OH that's adding on to the more substituted carbon and a hydrogen. And so you form your enol, and then it tautomerizes into the ketone. Reaction 5 is a hydroboration oxidation reaction. And so you're forming an aldehyde. This is an example of an anti-Markovnikov reaction. And so you're adding, again, an OH and a hydrogen, but this time your OH is adding on to the less substituted carbon. Another note I would like to put for this is that if it's an internal alkyne, that you would not form the aldehyde, but rather you would form the ketone. So for example, say I had this internal alkyne, and I'm doing that hydroboration oxidation reaction. So I would have, BH3 plus peroxide, followed by sodium hydroxide. You would form the intermediate, and so this is showing you how this is adding on as an anti-Markovnikov. So this carbon, oops, wow, that's supposed to be an alkene, not an or an alkyne and not an alkene. I have the ethyl, I'm adding my hydrogen onto that carbon, double bond, carbon, and my OH adding onto that carbon. So I'm adding the hydrogen to the less substituted carbon, or the more substituted carbon, and I'm adding my OH onto the more substituted carbon, so it has this anti-Markovnikov. And this is our enol. Tautomerizes very quickly into the ketone. So now I'm having 2 hydrogens and that ethyl group off that carbon, and then the carbon with the OH is now an oxygen double bond, so it's a ketone. So essentially, you're watching your electrons move in, and these move out to pick up a hydrogen, and you'll lose this hydrogen here. So just note that this is with the terminal alkynes, this particular figure. And so still going around the circle, reaction 6 here is a halogenation with 1 equivalent. This is going to be anti-addition. And so that is its stereospecificity, is an anti-addition. Try to make more room here. Let's move that down like that. For 7, you have a halogenation with 2 equivalents, and you're just going to add all the halides, right? And you're all the way to the alkane. For 8, this is the ozonolysis reaction that we just went through at the beginning of this video. This is going to be a terminal alkyne, so you are forming the CO2 and 1 carboxylic acid. Note that if it's internal, you're going to be forming 2 carboxylic acids. And then you have these reactions on the bottom here. First you have your alkylation, which we just went through. So you're alkylating and forming that internal alkyne on the bottom using reaction 9, which is the alkylation. You then have your dissolving metal reduction, your hydrogenation, and your hydrogenation with a poison catalyst. So adding in hydrogens in order to reduce this alkyne. So the poison catalyst one, the Lindlar's catalyst, which is reaction 12, so I'm going backwards now, but this is going to give you a cis alkene. And that's because it's doing a syn addition with the hydrogens, and so it'll give you cis. Your hydrogenation with hydrogen and palladium is going to reduce it all the way down to the alkane. So you're not stopping at the alkene, you're going all the way down to the alkane. And then if you have your dissolving metal reduction, so sodium and liquid ammonia, you'll be forming the trans alkene. And that is because this is an anti-addition when you're adding on those hydrogens. So that stereospecificity for that is anti. And so this is what I do. I just go through each number, I write little notes so I can remember how these reactions are going to be. You can also go through it and make a table, and I highly recommend this as you're going through Organic Chemistry 1 and 2, just making a table of all the different reactions you have. So like, what kind of compound are you starting with? Well, I'm starting with a terminal alkyne, for example. Okay, so what kind of reagents, if I add to a terminal alkyne, what would happen if I add ozone followed by water? So one of the reactions we just learned. Well, if it's a terminal alkyne, the result will be CO2 and a carboxylic acid. And then you can write a bunch of notes on here. And so whatever helps you at the end of the day to remember these reactions, either using that picture from the end of the textbook or making a table, do it, because you're going to be learning a lot. I'm adding into e-learning a table, a Word document table that you can fill in as you work through these. Chapter 11, we will be pretty much going over synthesis of all the reactions we've learned thus far and just focusing on synthetic routes, retrosynthesis, etc.